Greetings. In the previous video, I managed to calculate points 1, 2, 3 of my dual cycle and also uh, calculated information on heat transfer and work for processes 1, 2, and also for process 2, 3. Now, what we shall do here is to move to process 3, 4. Now, in process 3, 4, some fuel is being injected into the cylinder, and depending on how long would that injection last, would point 4 be further away from point 3. So, usually this is given as a volume ratio between points 4 and 3. And so what we do here is to have our knowledge, and we know that we are told that V4 over V3, V4 over V3 equals 1.209. This is the information we are given, which is also, since there's no change in mass, it is V4 over V3. The process 3-4 is constant pressure. It's, as they call it, isobaric. And now we have a knowledge of specific volume at point 4. So V4 would equal V3 times 1.209. That is V3, which is 0.04757 times 1.209, and therefore V4 is 0.05751 cubic meters per kilogram. And we also know that P4 equals P3, and that is 84.51 kilopascal. So with the knowledge of pressure and specific volume, now we can calculate T4. T4 equals P4 V4 over R. PV equals RT. And the outcome is P4, which is 84.51 times V4, which is 0.05751, and divided by R, 0.287. And the outcome for T4 is 1620. 1620 Kelvin. Once we have these values, we are in a good position to just fill in the next row for our table. And for P4, it is 84.51, which equals P3. T4, we just calculated it to be 1620. V4, we learned that it is 0.05751, and the rest of the cells may be read from the table just with the knowledge of temperature. And the values would be U4 is 13, 16.96, H is 17, 82.0, and PR is 834.1, and VR is 5.574. These are the values for point 4. We have all the knowledge for point 4. We are also in a good position to calculate the processes which happen at point between 3 and 4. You see, if we write down our equations between points 3 and 4, between 3 to 4, in this line, what we have is M4 E minus M3 equals 0, U3, U4 minus U3 equals Q34. Of course, there is heat transfer because we are injecting heat, but there's also constant pressure work. So minus W34. And the equation for the second law is that S4 minus S3 equals Q34 over TB. That's all, but we don't use it usually for our Gauss cycle calculations. Now, the point here is that we have work here, both work and heat transfer. But work is constant pressure work. So it is P, either 3 or 4 times V4 minus V3. And the interesting point is that P4, V4, you could add it with U4, P3, V3, you could add it to U3, and therefore Q34 would be H4 minus H3. So inserting values into this equation, Q34 would be 1782.0 minus 1443.6, and that equals 338.4 kilojoule per kilogram. And you could also calculate work for this process, which I would just do it here. And W34 is P, either 3 or 4. Let's write it 3 times V4 minus V3, and that equals 84.51 times 0.05751 minus 0.04757, and the outcome for W34 is 80.36 kilojoule per kilogram. So we have calculated both heat transfer and work for process 2, 3, 4. It's also a good practice to draw a table for different processes. We did draw a table for different points and properties, but there are also processes, and it's good practice to just write process properties. That means heat transfer, work, delta U and delta H for different processes, and check if all values would match. I mean, finally, what we should get is that all heat transfers added together should equal all works added together, that their sum should be the same for the cycle, and also delta U for the cycle should be 0. That just checks if all our calculations are in fact correct. Now, what we already have is that for process 1, 2, Q is 0 and work is minus 460.51 and delta U is 460.51. The delta U, I mean final U minus initial U. For process 2, 3, we learned that the Q is 384.36. Work was 0, and therefore delta U was 384.36. The unit here is kilojoule per kilogram, and the unit here is also kilojoule per kilogram. Both units are kilojoule per kilogram. For process, of course, delta H is irrelevant in these two cases. It's only relevant for process 3, 4. For process 3, 4, Q is 338.4. Work is 80.36, and delta U is 258.02, and delta H is 338.4. So we shall complete the rest of this table once we know point 5 properties for point 5, and then we could complete 2 rows of this table and also add columns together to see if they would all match. So let's move to process for 5. What are our knowledge on point 5? There are 2 ways to reach point 5. The first knowledge is that its specific volume equals 0.1, that of 0.1, and the second is that we are on an isentropic process from point 4. So we can just write down the specific volume for point 5, which equals that of 0.1, which is 0.861. And now we shall move to the isentropic process for this point, just from the knowledge of point V1. And what we get is that VR5 equals VR4 times V5 over V4, and this equals 5.574 times V5, which equals V1, 0.861 divided by 0.05751, and therefore VR for point 5 would be 83.45. And with this knowledge, we could go to the tables and just fill in a few columns. This is VR5, and that was 83.45 as we calculated it. Now, let's move to the other rows, and we would learn that T5, this one we have to interpolate. There is no way to bypass it. So T5 is 655.5. Then U5 is 477.5. H5 is 665.7. And PR is 22.56. The only remaining unknown is P5, which once we know PR5, it's very easy to calculate it. That's how we do it. P5 equals P4 times PR5 over PR4, since points 4 and 5, since points 4 and 5 are on the same isentropic line. And the outcome is 84.51 times 22.56 divided by 834.1, and the outcome is 218.7 kilopascal. Now, 218.7 kilopascal. Now, the two processes 4, 5, and all we are left are two processes here in this table, which are processes 4, 5, and 5, 1. The two very easy knowledge that we have about these two processes is that for process 4, 5 is adiabatic, so Q is 0, and for process 5, 1, work is 0 because, as is assumed, there is no movement of the piston. So with these two values, all we need to do is to calculate delta U for these two processes, and once we know delta U, all we would need to have is one would equal Q and the other would equal W. For process 4, 5, delta U is minus 839.46, and the work is, of course, the 839.46, which work would be positive since the work is being done on the environment. Here, the value for delta U, the value for delta U is minus 263.43, and that is exactly the value for heat transfer, 263.43. It's just simple writing of the first law of thermodynamics, and delta U equals W in this case, and delta U equals Q in this case. The check that we have done, we are correct, is to sum all values of Q here If we add them all together, that would be 459.33. And the first law tells us that when you go through a cycle, um, sum of all work done is equal to the sum of all heat transferred. So, and if we add all these together, it would be 459.31, which is uh, good enough. It's equal. And when you go through a cycle, then there should be no change in properties, and therefore the sum of all these terms should be zero, which in fact it is. So we know that we have calculated all points and all processes correctly. They all match, and now we could move to the next step and start calculating the cycle properties. That means total work, total efficiency, and the rest. The final steps in our calculation of this cycle is to calculate the total work, which we have already done so, because the total work here is the work that we have gained from these two processes, 3, 4, and 4, 5, minus the work we have done to compress air to start with. So, and the sum is 459.31. So the total work, let's call it just W, equals 459.31 kilo joules, of course, per kilogram. And the total heat transfer, total added heat, would equal the sum of heat added in processes 2, 3, and 3, 4. And if we add them together, the total would be 722.76 kilojoules per kilogram. And these are the total work and the total heat. Divide them together. Efficiency, the cycle efficiency would be 459.35 divided by 722.76, and the outcome is 0.635, which means 63.5% is the efficiency of this dual cycle, which is of course far higher than what in reality one would get from any reciprocating engine, perhaps something between 20 to 30% would be good enough for a reciprocating engine, but remember, this is the ideal cycle. Everything is reversible and everything is ideal. So another measure that we usually calculate is mean effective pressure, and this is the pressure one would get for a cycle. It's a sort of average pressure of the cycle, which is calculated as work 459.31 divided by engine stroke, which is 0.861 minus 0.04757, and the outcome for MEP is 564.7 kilopascal. In fact, it just shows that engines of a similar um, volume, similar stroke, which one would give more power? And this is the value. Now, if this is, say, an 1.8 liter engine, then for a 1.8 liter engine, for a 1.8 liter engine, then the mass flow per cycle would be V over V, which equals 0.0018 divided by 0.861, and the mass flow per cycle is 0.00209 kilograms of air is the mass flow per cycle. Now multiply it by the work we calculated it, and W would be I just could write it down here, and W would be the mass per engine cycle, which is 0.00209 multiplied by the work that we calculated it, which is 459.31, and the outcome is 0.96 kilojoule. For every cycle, it produces this much useful work. Now, if the engine is run at 3,500 reps per minute, which is quite an ordinary revolution for an engine, which many engines have their best efficiencies, minimum consumption at revolution. Just like that, then the power produced is 0.96 kilojoules per rev times 3,500, which is revs per minute. And we know that every minute is 60 seconds, and all we should divide it by 2 since it is a 4-stroke engine, and for every stroke that for every 2 strokes that this cycle performs, there are 2 other strokes, which one intakes air and the other one pushes air out of the cylinder. So we have to divide by 2, which is revs per cycle. So a cycle, basically, every 2 revs would be 1 cycle of useful work, and therefore W dot would be 28 kilowatts. Well, this is as much as I could say about a dual cycle. I hope you have learned the basics of how to calculate this cycle. Do not forget to draw the diagram, but more important, please draw these two tables, one for point properties and the other for processes. And once you have filled this table, then you have everything for your calculations. You remember that they should match these two values. The total heat and the total work should equal, and also the sum of all changes in U should be zero, and this would just mean that all your calculations are good, well, and correct. Well, thank you very much for watching, and cheers.